Today we're going to start talking about the reason why we put salt on the roads in the wintertime when there's snow and ice on the road, or why we put salt in our boiling water when we're making mac and cheese. Okay.
Nobody does that anymore.
I do it.
Does what?
I do it.
Anybody that's anybody puts salt in their mac and cheese water before.
Mine tastes better. You're supposed to do all yours.
Yeah.
What about like just the easy mac that you just put in the microwave?
No, this doesn't count. All right. Today we're going to talk about, or start to talk about boiling point elevation and boiling point elevation and freezing point depression. And that should say depression. Does that say depression on your notes? Should say depression.
Nope, it says elevation.
Make that change. It even says it here, but that's weird. Okay. When we talk about boiling point elevation, we'll typically be talking about water in this class. We'll talk about some other liquids in AP, but what temperature does water boil at?
Craig got lead just fell completely out.
Perfect. So what temperature does water boil at? 100 degrees Celsius. Good. So there is something that we can do to water to get it to boil not at 100 degrees but at a higher temperature. We'll talk about that today. Also, when we talk about water freezing, what temperature does water freeze at? Zero. So there's things that we can do to get water to freeze at a lower temperature. So if we can get water to freeze at a lower temperature, and say that we've got some snow and ice on the road, we can do something to that snow and ice and get it to have its freezing point be much, much lower, which in turn causes the ice or snow to melt. All right, so we'll talk about that. I don't know if we talk about that later on today. Let's see here. When we talk about pure solvents, again, we're talking about like water or something. Again, water is the universal solvent. So I'll give you the temperatures, or at least you should know the temperature for what water freezes at and what it boils at. Electrolytes. What's an electrolyte? It's in your Gatorade. What's that?
Thanks, Craig. It's the stuff that refuels your body. Like,
What's an electrolyte?
it helps you sweat.
Helps you
A
sweat.
substance, when dissolved in water, that is capable of carrying an electrical current.
Okay, so what's an electrolyte?
I just told you.
In Gatorade, what is the electrolytes?
Sugar,
Not sugar.
salt.
The salt. It's the potassium, it's the sodium. It's, in other words, whenever you're exercising, at least if you're doing it right, you're sweating out these salts, the sodiums and the potassium. Colligative properties. We talked a little bit, or we started to talk about colligative properties. Here's one of them. Whenever we talk about colligative properties, there's a couple properties that are associated with this. One of them is the ability for a molecule to dissociate into more particles. And typically this takes place with ionic compounds. So like I had you guys dissociate compounds earlier. We had a quiz over it where you actually showed the net ionic equation for some things. But if I look at, say, sodium chloride has one sodium and one chlorine. If I dissociate that in water, I get a sodium ion and a chlorine ion. These are considered electrolytes. Now what's really important is it's not how big the particle is, but how many particles it actually can dissociate into. So sodium chloride, which was typically used to put on our roads, only came up with 2 particles. However, what's being used now, at least in Indianapolis or downtown Indianapolis, is this green salt, calcium chloride, because it'll dissociate into 3 particles. Now, you don't know what that number means yet. We'll talk about that tomorrow. But the more particles, the better it is that it will cause the boiling point to be elevated or the freezing point to be lowered. So making sure that we can still dissociate that's pretty important. Now, whenever you see something that is molecular or nonmetal with nonmetal, it will dissolve, but it will not dissociate. So I don't want you to look at something like this. What is this C6H12O6? Anybody know what that's called? Glucose. It's a sugar, one of the most common sugars that we probably talk about. But this stays together. The carbons don't break off, of the hydrogens and the oxygens don't leave either. So it stays as a molecule. It's a molecular compound. So when we place this into water, it'll dissolve, but it will not dissociate. Okay. And the reason why there's sugar in Gatorade, make it taste good. And also, what does sugar provide? Energy. Yeah. So this is the energy component of your Gatorade, which you really don't need after a workout, but you do need the ion replacement or the electrolyte replacement. But it would taste terrible if it were just filled with electrolytes. All right, now we have talked about molarity earlier in the year, but whenever we work with something like this, we have to work with what's called molality. Okay, so molarity is moles per liter. Molality is moles per kilogram, and the kilogram deals with the amount of the solvent. So again, when I talk about moles of something, that's the thing being dissolved. The kilogram or the liter is the amount or the thing that's dissolving. Now the reason why this is significant is because, again, when we talk about freezing point, depression, and boiling point elevation, we're changing the temperature. With molarity, we're generally staying at the same temperature when we do this reaction. And hopefully you remember from just general science that when, say, a liquid gets warmed up, what does it do? Does it stay the same volume, expand, or contract? It expands, okay? So when something warms up, it expands. So when you expand that 1 liter, I mean, it might be just not like 1.05 liters, but it does change the molarity. The nice thing about molality is it doesn't matter how much it expands because we're going based on weight. So it's the number of moles of the particles per kilogram of the solvent. So just a little bit different, okay? So, and molality is represented with a little m. So that's about the third. All right, and we'll do some examples here to help you prepare some malal solutions. We'll do that here once we turn the lights on. So we've got 2 examples there. So part of the homework is the 4s, and that'll make a little more sense after we do the examples. All right, calculations involving some colligative properties. We're going to do today some boiling point elevation calculations and some freezing point depression calculations. And it will make a lot more sense once I actually work it out on the board. However, the 2 equations that we'll be using, here's one of them, and I know you can't see it really well up here on the screen, but hopefully it's a little bigger in your notes, or at least it'll make sense once we try it. So we'll use this calculation, and again, I hate to point to it because I know it's really small for me right here, but we have delta T. What does delta mean again? The change. So it's a change in temperature, and if it has a little b as in boy right next to the temperature, that's dealing with boiling, so the temperature in which it boils at. And that's equal to Kb times m, all right? Kb is a constant. I don't know why in chemistry we call all of our constants with a K, but that's our constant, and we'll work with that unit here in a second. Then the other equation is similar to that, except it's delta T sub F, where F deals with the freezing point, depression. And it has a different constant as well for our Kf, times the M, which is, again, is the molality. So we'll work out some examples with that, and now's a good time to probably turn the lights on so it makes sense to what I'm telling you. Okay, so let me turn the lights on here. All right, let's take a look at page 3. Question number 1 says, or it asks, and we're looking at the practice problems on page 3. It says, how many moles of sucrose, which is C11H22O10, are there in a 2.33 molal solution made with 1,450 milliliters of water? So again, when we talk about molality, it's the number of moles per kilogram, okay, of your solvent. And we'll use water as our solvent for all of this. There's a couple things given. First of all, it told us that we had 2.33 molal, which again represents what? 2.33 moles of a 1 kilogram solution. Okay, so again, just like with molarity, keep the number with the unit mole. Okay. All right. Well, we don't have 1 kilogram of solution. We actually have 1,450 milliliters of water. So how in the world can we get that converted to kilograms? Okay. How do you do that?
Did you do the S3 before?
No, no gases.
Convert it to moles.
Don't convert it to moles. We want to get milliliters to kilograms.
Yeah, I was gonna say convert to moles and convert it.
Now, what'd you do on the test? Because I gave you a conversion, or at least, no, that was for centimeters cubed.
Equals
Nope.
1 kilogram. Centimeter.
1 milliliter equals
1 centimeter.
1 gram. Very good.
Yeah.
And that's for water only. Okay, so the density of water is 1 gram per 1 centimeter cube, or 1 gram per 1 milliliter. So whenever you see water, this is our conversion for that. So to get that converted, I bet a lot of you could probably do that in your head. So 1 milliliter equals 1 gram. Getting that to kilograms, we're going to put grams down there and kilograms up on top. Which one's bigger?
Kilogram.
Kilogram. And how many grams in a kilogram?
1,000.
1,000. So we have 1.45 kilograms. Okay. So now we have our 1.45 kilogram for our here. We also know that we have a 2.33 molal solution. And it wants to know how many moles. So we don't even need to worry about the formula for this. Even though sucrose is C11H22O10, it wants moles, not grams. So when looking at this, if we're looking for the number of moles, again, we have 2.33 molal, which is this. And we're actually looking for the number of moles, and we have our 1.45 kilogram solution, okay? So we need to find what this is, okay? So how in the world could we do that?
Wait, I don't know what
We're looking for moles, right? Okay, so molality, again, is moles per kilogram, which could be recognized as 2.33 moles per kilogram. So if I wanted to find out how many moles,
By 1.45.
so we're going to multiply this way, right?
Yeah.
And that's a good idea because we want the units kilogram to cancel out. So, and this is kind of working backward, just for the sake of space. So we have 1.45 kilograms times our 2.33 moles, and that's over kilogram. And again, here goes the arrows. So whatever that is.
Why is that?
So 1.45 times 2.33. So is that 3? We'll say 3.8. And what's my unit for that? Moles. The next one, or the second one, says how many grams, okay, so how many grams of magnesium carbonate are there in a 0.25 molal solution made with 850 grams of water? Okay, so first of all, probably the first thing that we should do is what? Write out the formula for magnesium carbonate. How do I do that?
Why do you need to know?
Because it's asking for the number of grams.
MgCO3.
So you want to know the formula so that we know what the molar mass for that is. And the other one, it didn't matter because we were just looking for moles. When we're looking for grams, we have to know what the formula is. And magnesium has what charge?
Let's do
Carbonate. So it's balanced as written, which is good. And probably wouldn't be a bad idea to find out what the molar mass for this is. So magnesium's 24.3 grams plus 12.01 plus 3 times 16. I think it's 24.3, is that right?
84.3. Yeah, you're right. 84.31.
So 84, good. So 84.31 grams, and that's per mole. All right, so it also says that we have a 0.25 molal solution, which is really that. And it said that we have 850 grams of water. So we need to change this to kilograms. So 1,000 grams in a kilogram. So again, if you need to show this step, please do. Okay. So we're looking for the grams. So the first thing we have to do is find the Before you find the grams, you gotta find the moles. Very good. So it's very similar to what we just did. So again, we're looking for the number of moles. We have our 0.85 kilograms. Okay. So how can I get moles all by itself? Let's multiply the 0.85 kilograms on both sides. So now we've got our 0.85 kilograms times our 0.25 moles over our kilogram. So we'll find out how many moles that is.
0.21.
Okay, so we have 0.2125 moles of magnesium carbonate. And then to find grams, what do you do from there? Convert. Very good. So we'll take our 0.2125 moles of magnesium carbonate. So it's a little bit of a tedious process here. What do we say, 84.31 grams? That's not too bad, I hope. So what is that, 17.9? So if I wanted to make a 0.25 mole solution, I would need 17.9 grams of magnesium carbonate and dissolve it in 0.85 kilograms of water. Awesome. It's good to be back in the math, right?
How many concepts are going to be on this test?
Oh yeah. Do what? No. Do it at Maddie. All right. Let's turn the page and look at page 6. And today we'll be using these equations here. However, all of the equations that we're working on today are molecular. Okay. Now, our real equation, even though I gave you this, it really looks like this, where there's an I in both of these equations, where we have the delta T sub B is equal to I times KB times M. The I tells us how many particles dissociate. Now, since we're working with molecular compounds, if I start with 1 mole of glucose, how many moles of particles will I have? 1. So this value really doesn't change, it's 1. Tomorrow when we work, or the next time we meet, when we work with ionic compounds, you're going to have to find out what that value is. This is actually called the Van Hoff factor. You don't need to know that for right now. But for everything that we're doing today, the value is 1, because it's a molecular compound. All right, so let's work one of those. Practice problem number 1. At what temperature will sucrose, or will a sucrose solution boil if it contains 175 grams of sucrose in 750 milliliters of water? Okay, so there's a couple things that we need to do first. The first thing is, let's decide which of these we'll use. Are we going to use delta T sub B or delta T sub F? The B, okay? So we know that we're eventually going to use that.
Wait, how do you know?
How do you know? Yeah, that's a good question.
What?
It says boiling.
Boiling, very good. So that's what the B is. That's what I said. The hardest part of this whole problem is deciding whether you're going to use B or F. So B is boiling, F is freezing. So if it says in the question, what is the new freezing point? So we do have we have 175 grams of our sucrose, that is C11H22O10. Okay. So again, if we're going to find the molality, what do we do here first, Beth? So what do we need to do first?
Plug it in the equation.
No, Beth. We have to get it to
convert
moles.
In mole. I just said that, Craig.
My bad, I didn't hear you. So we have to find out the molar mass. So we have 11 of those, 22 of those. And of course, 10 of those.
Huh?
Exactly. And the molar mass for sucrose is 314.
I already can't see.
We just shut up, Maddie.
All right, so the molar mass for the sucrose is 314. So 175 divided by my answer. So it's equal to 0.5 by 5, we'll say 7 moles. Okay. So that's how many moles of the sucrose we have. If we're going to find the molality, okay, if we know we have 0.557 moles, how much water do we have that we're going to dissolve that in?
750 milliliters.
750 milliliters, which is how many kilograms?
Is it
7.5.
0.75?
Yeah,
Okay.
something like that.
Now, again, if you need to do that work, then do that. Okay. Yeah, you move the decimal and change the unit. And we did that on an earlier problem, so that's why I don't want to necessarily show it to you. But if you need to show that, then do that. Okay. So 0.57 or 0.557 divided by 0.75. So that gives us, what is that, 0.74? We'll say 2. And that's little m, molality, which is moles per kilogram. Okay. So now we finally get to use our equation.
What?
I know, right?
I give up.
No, don't ever give up.
Why?
So delta T, and again, this is sucrose, or a molecular compound, so the multiplier in this case is 1, because it is a molecular compound.
So we're finding delta T.
We're finding delta T,
Why is it 1? And what is 1? The I or the J?
the I in Van Hoff factor.
And I.
The K is a constant, which is,
Wait, why? Wait. What's for I?
It's a 1.
Why is it 1?
because it's molecular, it doesn't dissociate. Molecular compounds, things that are made up of carbon, hydrogen, and oxygen.
So anything other than that is not 1.
Yeah. And, you know, I'll even be nice, but you gotta read the question. I'll put in there, what is the new boiling point for the molecular compound, blah, 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 or for the ionic compound, blah, blah, blah,
And if
blah,
it's
blah.
ionic, what number is it?
We'll talk about that tomorrow. That's not today. So everything's molecular
So
today.
everything's 1
Today.
So we don't even need the I then.
That's why it wasn't in the notes, but yeah.
Okay.
But you're getting it, I like it.
I think I got it.
All right, so our Van Hoff, or our constants, 0.51, and you'll notice that the units for this are kind of strange. It's degrees Celsius times kilogram divided by mole, which is the inverse of our molality. And I would recommend that while you're working these out, just leave it like this. Instead of writing little m, just write it out as molality. So our molality here is 0.742, which you just calculated, divided by kilogram. Okay. So what units can cancel out here?
Kilograms and moles.
Kilograms and moles. Okay. And that'll give us a value which has a unit of degrees Celsius. Very good.
I got 0.378.
I like it. So we have 0.3, we'll say 379. How's that? Okay. Now, here's my question. Okay. That is our delta T sub B. And we're looking for the new boiling point. So is my new boiling point less than 1 degree?
Yes.
No. It's my change. That's what the delta means. It's the change. It's the temperature in which water boils at what temperature again? 100. So now adding this much sugar, it boils at 100.379.
That's hot.
So since we are elevating the boiling point, you will add whatever the boiling point is.
How do you know you're elevating it?
You just explained that, didn't you?
Yeah, whenever we add something to water, it'll either cause the temperature of the water to boil at a higher temperature or freeze at a lower temperature.
So boiling, you're always adding.
We'll always add to 100. Okay.
And freeze,
You
you
will subtract.
Subtract from
Zero.
0, not 100. Very good.
So it's what?
What?
Huh?
What?
Because water freezes at 0.
Correct. And hopefully this next one's a freezing.
Yep.
It is. Very nice.
We have to include that in our answer.
Yes, make sure that you do this final step, okay? Because the question asks, at what temperature will the sucrose boil? And if you left it as 0.379, that's pretty cold. Okay. So again, this represents the change. Number 2. Number 2, it says, at what temperature will it, and I don't know why I have an N there. At what temperature will a methanol solution freeze if it contains 55 grams of methanol in 1,200 milliliters of water? So, again, which one are we using? Delta T sub B or delta T sub F? F. Gotcha, get it? I like it. So we need to first of all find the molality. And let's see, we have 1,200 milliliters of water, so how many kilograms of water is that?
So wait,
Okay.
the last problem, why did we even do the first step?
First step.
Oh,
What-
never mind.
We're doing it for this one as well. So methanol, we have 55 grams of that, and that's CH3OH. So we need to get that to moles. And what is that? 12.
It looks so funny.
What's that?
What?
Like the, putting the OH.
Oh. And what is all that? So 32. So the molar mass is 32.04 grams. So 55 divided by that. So we get about 1.7. We'll say 2. Okay. So we'll place that up here. What'd you do? So 1.43 is my molality. Okay. So once I have the molality, make sure that you pick the correct equation. So delta T sub F. Again, the I is what today? 1. Because if I place this in a solution, it'll dissolve, but it won't dissociate. The constant is not the same as the one that we used before, but it's the freezing, which is different, a lot different. So 1.86.
Who came up with
Degrees.
that constant?
What's that?
Who made that constant?
I'm not surprised.
Whoever first played with this.
I just don't see, like, is it really the same every time?
What's the same? Eh?
Like the constant?
For water it is. And what will our unit be again? Temperature?
Celsius. Right?
What's that?
Celsius?
Yeah. So 2.66. Very nice. Everybody hear that? So this is our change in our freezing point. So,
Just make it negative.
well, not everything freezes at 0, so you want to get in a good habit. So we have 0, and so it'd be negative 2. So again, when you are doing the freezing point, subtract from 0, and again, be sure to show that. That'll be worth a point. That's an easy point you don't want to miss. All right. All right. So the homework, the 4s and the 5s. Woo.